Alright, so I want to talk to you about some general trends of the periodic table introductory. So you get the idea, just a little introductory video. Alright, a couple of trends we're going to talk about. The first one's going to be atomic size, and we'll get to ion size later. Ionization energy and electronegativity. These are three very common trends that you're supposed to be familiar with in the periodic table. So, first trend, it has to do with atomic radius or atomic size. The key thing that basically dictates what that trend is going to be is what's called effective nuclear charge. The effective nuclear charge, or Z, is the nuclear charge experienced by the outermost electrons. You see the definition right there. That's what effective nuclear charge is. So what that means is the more protons you have in the nucleus, the greater the pull on the outer electrons. The greater the pull on the outer electrons, because the increased number of protons will mean the atomic cloud or electron cloud will get smaller. So what does that look like? Really, is it as you go across the periodic table, you take the third period where you start with sodium, right? Sodium has 11 protons, 12, 13, 14, 15, 16, 17 protons. So the reason why atomic size decreases as you go across a period from left to right has to do with effective nuclear charge. You add a proton and an electron as you go across the periodic table. So sodium has 11 protons, 11 electrons. Magnesium has 12 protons and 12 electrons, but the electron feels a greater pull and the electrons are pulled in closer because of the additional proton. So what does that mean? As you go this direction across the periodic table, the atomic size or the radius of the atom or the atomic cloud gets smaller. Key thing to remember is this. Make it real easy for you as far as trends go. The largest element in the periodic table is francium. So imagine there's a flag there and it has the word size written on there. The flag for atomic size is stuck right there. Francium is by far the largest. Therefore, if you're comparing two elements, if I'm comparing aluminum or phosphorus, trying to figure out which one's larger, the one that's going to be closer to that flag or that point automatically is going to be larger. If the element is farther away, like magnesium and beryllium, well, magnesium is closer to the flag for size. If you just remember the largest one and then use that as your reference point, beryllium would obviously be smaller than magnesium. So the overall trend for atomic size, basically, since the largest element, francium, is there, the overall trend for size, if you had to draw a sketch and arrow like I asked you to do, is size increases as you go down, or as you go left to right, it decreases. So atoms get smaller as you go across a period because you're going from left to right, because the nucleus contains more protons. The higher charge attracts the electrons strongly, automatically making the atom smaller. That's the best definition of an effective nuclear charge. So a higher effective nuclear charge, the electrons are held more tightly. Why do atoms get larger as you go down the group? Because you're adding a new electron shell. You're adding another layer. So if you have this layer here, you add a whole nother shell, automatically they get a little farther away, or the atom has to get a little larger. If you look here, here are the actual sizes listed. Cesium, francium is not listed on this. Cesium by far is the largest. If you look there, as you go this way, they get larger. As you go across a period, they get smaller. The general trend, though, just remember, is that direction. Okay. Electronegativity. The definition of electronegativity is the tendency of an atom to attract electrons to itself. So when you're in a bond, how strongly does that atom pull on electrons? Is it strong enough to pull the electrons, or not completely pull them away, but pull them closer to that element than the other one? Atoms that have a higher electronegativity have a greater attraction for electrons. Well, the trend is as you go from left to right, electronegativity gets larger, and as you go down, it decreases. Increases left to right, decreases. Easy way to remember the trend is this. The most electronegative element in the periodic table is fluorine. So imagine there's a flag for electronegativity there. So if I'm comparing boron and nitrogen, whoever's going to be closer to that flag will automatically be more electronegative. You can already tell from the values that are listed there. They're not going to give you a table with values on the AP exam that nitrogen is closer to fluorine than boron is. Same thing if you were comparing calcium and strontium and barium. The general trend without a list of the values, calcium would be closer to the flag, therefore it would be higher electronegativity than, say, if you were comparing it to barium. And you just have to know the general trend. Obviously these two are the same, but as you go up you notice that the electronegativity increases. Noble gases don't really bond. So since they don't gain any more electrons, they don't have a strong pull or a strong attraction to electrons, so we don't really count them when we deal with electronegativity. If you notice, they're off this periodic table. All right, last trend, ionization energy. What's the definition of ionization energy? Well, definition of ionization energy is the energy required to remove an electron from an atom, the outermost electron. So if you talk right here, here's a diagram right here. How much energy is required to take that electron and rip it off? That's what ionization energy is, because when you remove the electron, you're going to turn that atom into an ion. So, what's the trend? There's a few hiccups in this trend, but the overall trend is basically if you have successive electrons taken from the same atom, so you're not looking at the periodic table, but you're taking the same element, each time you remove an electron from an element, it increases, the ionization energy increases. When you're specifically talking about the periodic table, as you go across a period, it tends. See the magic word there, tends? So it tends to increase across the period, and I'll show you a couple instances where it doesn't. And it also tends to decrease down a group. But there are some irregularities at half-filled and filled sublevels, and we'll talk about why those are in class. So if we look right here, who has the greatest ionization energy? If I was going to put a flag, I would put a flag where fluorine is, i.e. Same idea. If you're comparing the ionization energy of tin versus phosphorus. Tin and phosphorus. Phosphorus is closer to the flag, or the element that we know as the highest ionization energy. Therefore, if you had to rank them, you would say phosphorus would have a higher ionization energy than tin. If you were comparing calcium and potassium over here, calcium is closer to the flag, therefore it has a larger ionization energy. Now, if you look at the overall trend, there are some inconsistencies, especially with ionization energy. Take period 2. You start with lithium as you go across, it's 520. You get to beryllium, it's 899. You see a drop. When you go from 2A to 3A, or group 2 to 13, there's a drop because it's actually easier to remove a single electron from boron than it is the ones that are paired in beryllium. Same thing happens when period 3. Sodium, 496, magnesium, 738, and bam, aluminum, it drops. It drops to 577. As you go across period 2, you go boron, carbon, nitrogen, right? It's increasing. Bam, that single electron from oxygen, the single electron, where there's 4 electrons in that shell, that P shell, that electron can be easily removed. That's why you see a dip in the ionization energy, and then it increases again when you get to fluorine. You see the same dip as you go from phosphorus to sulfur. The ones that you really need to be aware of are beryllium to boron. There's a drop in ionization energy, and magnesium to aluminum. Those are the 2 most common that you'll see discussed typically. Here's an easier way to see it actually. If you look at it this way, if you're tracing as you go across ionization energy across a period, it tends to increase. Lithium to beryllium up, drops down right there. There's one exception. Carbon up, nitrogen up, back down, and then fluorine. And then if you include the noble gases, it increases. It's really hard to remove an electron from noble gases. Same thing with period 3. Sodium to magnesium, then you see it drop again because it's easier to remove an unpaired electron from the 2p shell, or in this case the 3p shell. Silicon, phosphorus, again another little drop, and then it increases. So the key thing when they ask about exceptions, Boron and aluminum come up quite often. Sometimes they mention oxygen and sulfur. You just have to be aware of the structure of the periodic table. So if you had to overall sum up the trends, basically the trends for fluorine is has a high electronegativity and obviously a high ionization energy is fluorine. So the closer the elements are to fluorine, the greater those values are going to be. So overall, if you sketched out a periodic table, rough sketch here, the trends, I would have a flag here for size, and I would have a flag here for ionization energy and electronegativity. So we have those elements. So the overall trend for size increases as you go this direction. So the closer you are to francium, the larger your size is going to be. If you're talking about ionization energy and electronegativity, the closer you get that direction, because it will be fluorine. Closer you are to fluorine, the greater ionization energy, or the closer you are to fluorine, the greater the electronegativity. All right. Have a good evening. Enjoy the rest of your weekend. I'll see you on Monday.